Example 1, a particle moves in the xy plane so that at any time t, the position of the particle is given by x of t, and there's an equation given, and y of t, and another equation given. They want us to find the velocity vector when t equals 1. So if we're given position, then that means we're going to take its derivative to get velocity. So the velocity vector will be x prime of t, comma, y prime of t. And so the derivative of our x of t equation will be 3t squared minus 8t by using our power rule. And the derivative of the y of t equation will be 4t cubed plus 6t squared. Please forgive my handwriting with the stylus. Okay, so this is our velocity vector, but then they also give us that they want the time to equal 1. So we have to plug 1's in for our times here. So that's going to be 3 times 1 squared minus 8 times 1, and 4 times 1 cubed plus 6 times 1, which will give us negative 5, 10, which is the solution to 1a. 1b says, write the equation of the tangent line to the graph when t equals 1. Okay, in order to write a tangent line equation, we're going to use point-slope form. We're going to need a point, and we're going to need a slope. If we know the time is 1, to get the point, we can say x of 1 equals 1 cubed minus 4 times 1 squared. That will give us x equals negative 3 for our point. Y of 1 will give us our y coordinate, 1 to the 4th plus 2 times 1 cubed plus 5 gives us a y value of 8. So our point is negative 3, 8. Now, to find the slope, we have to figure out what dy dx is. Dy dx. So the derivative of y with respect to t over the derivative of x with respect to t. Now, we already figured out what these derivatives were in part A. So it's going to be your 4t cubed plus 6t squared over 3t squared minus 8t. And then we plug in the time of 1, which we already did up here. So we're going to end up getting a dy dt such that time equals 1 will be 10, and dx dt such that time equals 1 will be negative 5, and 10 divided by negative 5, of course, is negative 2. So our equation for the tangent line will be y minus 8 equals negative 2 times x plus 3. And that is the answer to 1b. Now, find the acceleration vector when t equals 1. That just means we're going to take the velocity vector that we got in part A and find its derivative. So it'll be 6t minus 8 and 12t squared plus 12t. And we plug in 1's to both of these, so 6 times 1 minus 8 gives us negative 2. And 12 times 1 squared plus 12 times 1 is 24. So there's our answer to part C. Alright, example 2. A particle moves in the xy plane so that at any time t, where t is greater than or equal to 0, the position of the particle is given by, and we have an x of t and a y of t equation. Find the magnitude of the velocity vector when t equals 1. Okay, so we're going to need to use the magnitude formula, which you need to know, square root of x prime of t, oops, that's the derivative of t of your x of t equation, squared plus y prime of t squared. Should look kind of familiar from pre-cal, kind of stemming off of your, oops, I lost a parenthesis there, Pythagorean theorem. So this is going to equal, well, we're going to need an x prime of t. What is x prime of t here? The derivative of our x of t equation, 2t plus 3. Now we're doing this when t equals 1, so if I plug a 1 in there, x prime of 1 will equal 2 times 1 plus 3, which is 5. Now I need a y prime of t, which is 3t squared minus 6t. And if I sub a 1 in here, 3 times 1 squared minus 6 times 1 is going to give me, see if I can, negative 3. So this is going to be, let's see, the square root of 5 squared plus quantity negative 3 squared, so that's going to equal the square root of 34, which is the answer to example 2. Alright, example 3. A particle moves in the xy plane so that x is equal to, we're given the equation, and y is equal to, and the other equation, where time is between 0 and 2 pi. The path of the particle intersects the x-axis twice. Write an expression that represents the distance traveled by the particle between the two x-intercepts. Do not evaluate it. Alright, the distance traveled, total distance traveled for parametrics we learned earlier this year, that's going to be your integral from starting point A to ending point B along your x-axis of the square root of x prime of t squared plus y prime of t squared dt. So, we're going to need an x prime and a y prime. So, x prime is going to be the derivative of our x equals equation. So the derivative of square root of 3 is 0, and the derivative of negative 4 cosine t is 4 sine t. Now we're going to take the derivative of the y prime equation, which derivative of 1 is 0, derivative of negative 2 sine t is going to be negative 2 cosine t. Okay, so those are what are going to be subbed into our formula. Now we just need to figure out what a and b are. Okay, we're talking about the distance traveled by the particle between the two x-intercepts. How do we find x-intercepts? X-intercepts occur when y is equal to 0. So I have my y equals 1 minus 2 sine t equation. I want to take that and set it equal to 0 to find my x-intercepts. So, if I add 2 sine of t to both sides, and divide by 2 on both sides, I get the sine of t is equal to 1/2. The inverse sine of 1/2 would equal time. And so, from your unit circle, the sine is equal to 1/2 at pi over 6 and 5 pi over 6. Remember, that's your y coordinate on your unit circle, and we're working with time between 0 and 2 pi. So, this will be the integral from lower limit pi over 6, upper limit 5 pi over 6 of the square root of our x prime, which is 4 sine t squared, plus our y prime, negative 2 cosine t squared dt. And we wrote the expression, but do not evaluate it. And again, I apologize for the messy handwriting with the stylus. I'm still trying to get used to this. Alright, example 4. A particle moves in the xy plane so that at any time t, the position of the particle is given by x equals equation, y equals equation, where time is greater than or equal to 0. For what values of time is the particle at rest? A particle is at rest when the velocity is equal to 0. If I have a position equation, I take its derivative to get the velocity. So x prime of t is 6t squared minus 30t plus 36. And y prime of t is equal to 3t squared minus 6t. Okay, so if I want these velocities to equal 0, both my x and my y velocities need to be 0, otherwise I still have some kind of motion going on, vertical or horizontal. So I'm going to set both of these equations equal to 0 and solve them using my good old algebra skills. So how am I going to solve this one? Well, everything's divisible by 6, so let's divide both sides by 6 to start. And is it factorable? Yes. It's a non-calculator problem. Everything's coming out nicely. T minus 2, t minus 3. So that gives us a time of 2 and a time of 3. Over here, I can divide everything by 3. So t squared minus 2t, factor that, t times t minus 2, so I get a t value of 0 and a t value of 2. So, what does this mean? Is my particle at rest at time 0, 2, and 3? No, only at the ones that they both share in common, because both the x and the y have to be motionless in order for the particle to be completely at rest. So that's only going to occur at time t equals 2. Alright, example 5. I'm wondering if I can fit it here. We'll see what we can do. A particle moves in the xy plane in such a way that its velocity vector is, and we're given this velocity vector, if the position vector at time t equals 0 is 7, negative 4, find the position of the particle at time t equals 1. So, we are given a velocity vector, and we need to find the position. Okay? So what do we do to our velocity to get position? We integrate it. So, x of t will equal the integral of 3t squared minus 4t dt. We're going backwards from velocity to position. So that's going to give me x of t. Now we're doing power roll backwards. Add 1 to the power on the t. That's going to be t cubed. Multiplied by the reciprocal of that new power, 1/3 times the 3 already there, just gives us a 1. Add 1 to the power on the t here, t squared. Multiply by the reciprocal of that new power. Negative 4 times 1/2 will be negative 2. And then we, of course, need plus c. Now, we do need to figure out what c is, and that's why they gave me this bit of information in the problem. I know that at the time 0, my x value is 7. So I'm going to plug that in. 7 is my x, when my time is 0. So 0 cubed minus 2 times 0, oops, trying to write small, squared plus c. Well, the 0 cubed, the 0 squared, that's all gone. 7 is equal to c. So now I know my x of t equation is t cubed minus 2t squared plus 7. Now I'm going to go and do my y. y of t is equal to the integral of 8t cubed plus 5 dt. So y of t is equal to 2t to the 4th plus 5t plus c. And again, I know that my y value is -4 when my time is equal to 0. So that makes my c value equal to -4. So what am I actually trying to find here? The position of the particle at time t equals 1. So I'm going to say x of t equals t cubed minus 2t squared plus 7. And what is my time? 1. So plug in 1's for both of those t's. So I'm going to have x of t is equal to 1 cubed, which is 1, minus 2 times 1, which is 2, plus 7. So that's going to give me an x value of 6. Then I do that likewise for my y value. Y of t is equal to 2t to the 4th plus 5t minus, oops, that's a t, minus 4. So plug in a 1. Y is equal to 2 plus 5 minus 4, which means y equals 3. So the position of the particle at the time t equals 1 is 6 for x, 3 for y. That's the answer to number 5. Okay, we haven't needed to use a calculator for anything up to this point, and number 6 is an example of one where we would use a calculator. An object moving along a curve in the xy plane has position x of t, y of t at the time t, with a dx dt equal to sine of t cubed and a dy dt equal to cosine of t squared. At time t equals 2, the object is at the position 7, 4. Write the equation of the tangent line to the curve at the point where t equals 2. Okay, tangent line means we're going to use point-slope form. We're going to need a point and we're going to need a slope. Well, we're given a point 7, 4, so we can use that. But we need to find a slope, dy dx. So that's going to be the derivative of y with respect to time over the derivative of x with respect to time, which they just so happen to give us in the problem. So that's going to be the cosine of t squared over the sine of t cubed. And what am I going to plug in for those times? Well, since I'm using the position 7, 4, that occurs at time t equals 2, so I'm going to plug in my 2. So it's going to be cosine of 4 over sine of 8, 2 to the 3rd power. So my tangent line equation will be y minus 4 equals the cosine of 4 over the sine of 8 times x minus 7. And no, we didn't really need a calculator to get that exact answer. Alright, B. Find the speed of the vector at time t equals 2. Okay, speed is going to be magnitude. So we're going to do the square root of x prime of t squared which is the same thing as dx dt, so sine of t cubed quantity squared plus y prime of t squared, so that's going to be cosine of t squared quantity squared. So at time t equals 2, we're just plugging in the 2 for both of those time values, so that's going to be the square root of the sine of 8 squared plus the cosine of 4 squared. That would be an exact answer if that's what they wanted. This is a calculator problem. They're wanting you to plug it in and round it to 3 decimal places. 1.186 is what that comes out to. Be sure your calculator's in radian mode. Okay, part C. For what value of time, where time is between 0 and 1, non-inclusive, does the tangent line to the curve have a slope of 4? Find the acceleration vector at this time. Okay, so we know that the slope, dy dx, is equal to the cosine of t squared over the sine of t cubed. We established that in part A. We're going to set that equal to 4, and we want to know when does that happen. Well, this is a calculator problem. We're not going to solve this algebraically. You're going to take cosine of t squared over sine of t cubed using proper parentheses and put that in your calculator into y1. You're going to take 4 and put that into y2, and you're going to look for the intersection in your calculator by going to second and the calculate menu, option 5. So when you do that, you're going to come up with a time of 0.616486622, and I used all those decimal places because that's not the final answer to the problem. We also have to find the acceleration vector at this time, and we don't want to be guilty of premature rounding here. So the acceleration vector is x double prime of t, y double prime of t, and so we're going to take the derivative of the derivative equation that we were given initially in the problem, which means we're going to have to use our chain rule. So the sine of t cubed was x prime, so we're going to take the derivative of the outside function, which the derivative of the sine is the cosine, copy the inside function, which is t cubed, and multiply by the derivative of the inside function. The derivative of t cubed is 3t squared, cosine of t cubed. Then, same thing for the y's. The y dy dt equation, which is the same thing as y prime, was cosine of t squared. So the derivative of the cosine is a negative sine. Copy the inside function, t squared, and take the derivative of the inside function, which is negative, well, it's going to be 2t, but multiply by the negative sine, and then that inside function is still here, t, was it squared? Yes. For the y. Okay. So there's the acceleration vector, but they want it at this time. So I'm going to store this value that I got as x and sub it in for all of these t values in my calculator, which is a bunch of plugging and chugging, and I get 1.109 negative 4.57. Okay, last one. Find the position of the particle at time t equals 1. And of course, we saved the best for last here. This problem is a little bit challenging. You will see ones like it again, so you may want to go over it. Time t equals 1. Alright, we don't have information in the beginning of the problem at t equals 1. We have information about time t equals 2. So we're going to kind of go in here a little backwards and use a little bit of clever thinking to solve this problem. We're going to look at the integral from 1, because that's what we want, to 2, because that's what we have some information about from the given in the problem, of v of t, because I want the position, so I integrate velocity to get position. I was given the velocity, the derivative equations in the problem. And according to the first fundamental theorem of calculus, this is going to be equal to the position at time 2 minus the position at time 1, because the antiderivative of velocity is position, and then we take the top number, plug it in, subtract the bottom number plugged in. Okay? So, there's two ways we're going to have to go through this, the x direction, and then we're going to have to do the same thing again with the y direction. So, these will work the same way. So, integrate from 1 to 2. The velocity for x was the sine of t cubed dt, and that's going to give me my x position at 2 minus my x position at 1. Now, x position at 2 I know. It's 7. They gave me that in the problem. I'm wanting to know x of 1. Notice x of 1 is the only unknown in this problem now. So, if I add x of 1 to both sides and then subtract the integral from both sides, I get x of 1 is equal to 7 minus the integral from 1 to 2 of the sine of t cubed dt. And you can do this in your calculator. Round to 3 decimal places, you get 6.782. And y direction works the same way. I'm going to take the integral from 1 to 2 of the cosine of t squared. That's going to give me y of 2 minus y of 1. I know y of 2 is 4. They gave that to me in the problem. So, I'm going to add y of 1 to both sides, subtract the integral from both sides. Y of 1 is equal to 4 minus the integral from 1 to 2 of the cosine of t squared dt. Ooh, running out of space here. Y of 1 will equal 4.443 when you type that in your calculator. So, the position is really the coordinate pair, 6.782, comma, 4.443. And that's the answer to that problem. If you have any questions or problems, please come in for tutoring. I'm all finished with duty, I believe, for the entire rest of the year, so I should be available before school and after school every day. Or you can email me. So, hope that y'all are having a good time with vectors. Bye.